Welcome to the channel. Thanks for joining us, your one-stop for everything AI. If this is your first time, please consider subscribing and ringing that all notification bell. Go ahead and share your thoughts in the comments. We are highly interested in your feedback. The integration of artificial intelligence and robotics represents an epochal shift in technological capabilities. This powerful combination has equipped robots with unprecedented skills, rivaling humans across diverse job fields. At the frontier of this revolution is Eureka, an AI agent developed by Nvidia Research to autonomously teach robots complex new skills. Eureka signifies a paradigm change in how robots can learn. By harnessing the algorithmic prowess of AI models like GPT-4, Eureka automates the formerly manual process of coding robot training curriculums. This unprecedented level of automation has enabled Eureka to train robots in a vast repertoire of nuanced skills, like smooth pen spinning tricks and dexterously opening drawers. Across extensive benchmarks, Eureka consistently outperforms the best human-designed training programs. Its self-enhancing architecture continually improves by analyzing simulation outcomes. Eureka's flexible simulations-based training methodology is unlocking remarkable new capabilities across diverse robot types and applications. This synergistic combination is disrupting various industries and redefining the future of automation. The relentless pace of technological innovation never ceases to amaze. An AI behemoth, Nvidia has raised the bar once again with its latest creation, Eureka. Eureka signifies a quantum leap in enabling robots to learn complex motor skills and tasks. This AI-powered agent can autonomously generate algorithms to train robots via reinforcement learning, a trial-and-error process similar to how humans acquire new skills. This breakthrough became possible by tapping into the phenomenal power of OpenAI's GPT-4, the largest language model to date. Eureka leverages GPT-4 to automatically write code and define rewards that guide the training of robots. Nvidia has been at the frontier of innovation for decades, with pioneering work in AI, graphics and autonomous machines. Nvidia Research, the company's hub for cutting-edge R&D, led the development of Eureka. The team responsible comprises scientists across disciplines including AI, robotics, reinforcement learning, graphics simulation and generative models. By combining their expertise, they were able to architect Eureka's distinct capabilities. An integral technology powering Eureka is Isaac Gym, a simulation platform for robotics training created by Nvidia. Isaac Gym provides a virtual environment where different manipulations can be simulated at scale, enabling large-scale training of reward algorithms by Eureka. Eureka represents an ingenious fusion of two branches of AI generative models and reinforcement learning. Here's a closer look at how it achieves its magic. Eureka taps into the raw power of OpenAI's GPT-4, the largest language model created thus far. GPT-4 has displayed an uncanny ability to generate human-like text and code. Eureka exploits this prowess to automatically generate code-defining rewards and algorithms for robot training. This alleviates the need for human experts to manually formulate these complex programs. By querying GPT-4, Eureka can produce thousands of potential reward functions and training regimens tailored to specific robot skills. This enables a massive expansion in the scope of what robots can be trained for. Eureka leverages Isaac Gym, which allows modeling various robot manipulations in a virtual 3D environment. Here, the reward programs crafted by GPT-4 can be tested out extensively through simulated reinforcement learning. Robots can undergo digital training across millions of instances in the virtual gym. This simulation-based approach confers significant advantages. The accelerated pace of digital training exceeds real-world physical trials by orders of magnitude. The complete safety of a virtual environment also allows limitless experimentation. A distinctive capability of Eureka is its ability to recursively enhance itself. The system analyzes the outcomes of training simulations to determine the efficacy of the generated reward algorithms. These insights are fed back into GPT-4 to improve its formulation of reward functions. With each iteration, GPT-4 gets better at coding rewards tailored to specific robot skills. This self-improving architecture allows endless refinement of Eureka's training programs. Robots can thus be taught ever more complex skills with continually improving efficiency. Eureka has unlocked an expansive palette of skills in a range of robot types, from dexterous humanoid hands to robotic arms commonly used in manufacturing. This demonstrates its versatility as a generalized robot training framework. One of Eureka's most striking accomplishments is training a robotic hand to perform smooth pen spinning tricks, such as the Devil's Sonic and back-around corkscrew. These complex maneuvers require nuanced coordination that mirrors human motor skills. In head-to-head comparisons, the Eureka-trained hand matched or exceeded pen spinning proficiency levels achievable by human experts through months of practice. This is an astonishing validation of Eureka's capabilities. Eureka enabled similar feats of dexterity, such as adeptly handling scissors and precisely controlling robotic fingers, to opening drawers and cabinets. Collectively, these achievements signal that Eureka can impart human-like motor skills to robots. While specifically designed for factory automation, conventional industrial robot arms have limited versatility for delicate jobs. Eureka breaks this barrier by teaching such robots greater dexterity. As examples, Eureka has trained standard robot arms to sweep debris, carry eggs without cracking them, and perform dexterous pressing of buttons. This could expand the usefulness of industrial robots for precise tasks alongside heavy lifting and assembly line roles. Eureka has instructed robots in an extensive repertoire of skills like catching balls, maneuvering quadcopters, walking bipeds, and manipulating block structures. The common theme is that Eureka can automatically formulate tailored algorithms to train robots for any well-defined task. Its training generalizability stems from GPT-4's innate skill at translating task specifications into suitable reward functions and training regimens. But does Eureka actually train robots better compared to traditional methods? Extensive benchmarks reveal that it consistently outperforms human-coded alternatives. Across 29 complex manipulations, Eureka's training algorithms surpassed human-designed ones over 80% of the time. On average, skills acquisition was over 50% faster with Eureka versus programs crafted by human experts. For pen spinning, Eureka compressed the training time from months to just a few hours. A greater than 90% efficiency gain. These metrics substantiate Eureka's uniqueness in enabling rapid and effective robot training. By relying on AI to automatically generate optimized curriculums, Eureka overcomes limitations of manual coding. The superior performance also highlights the untapped potential of large language models. Given appropriate framing, GPT-4 can produce highly specialized outputs like robot training algorithms rivaling human ingenuity. Eureka's flexibility in teaching diverse robots in all manners of skills is astonishing. But even more remarkable are the technological shifts it could catalyze and the tantalizing possibilities it unveils. A persistent challenge in robotics has been translating AI innovations into enhanced real-world capabilities. Eureka now provides an immensely powerful conduit for infusing AI into robotics. As AI algorithms and models continue advancing at breakneck speed, Eureka offers a pathway for translating these gains into smarter and more dynamic automation. Already, integrating GPT-4 has expanded Eureka's prowess. Future AI improvements could compound its capabilities even further. Many manual jobs like surgery, craftsmanship, cooking, and creative arts remain stubbornly difficult to automate because they involve intricate human motor skills. By enabling robots to attain sophisticated dexterity, Eureka expands the horizon of what automation can achieve. We could see robots trained for delicate surgical procedures, agile manufacturing of personalized products, food preparation, and even creative pursuits like drawing and dancing. For structured industrial settings and well-defined service roles, Eureka unlocks smarter automation. It allows easy reprogramming of robots for new tasks by simply specifying desired outcomes. Manufacturing robots could be rapidly switched from assembling one product type to another. Service robots may adapt on the fly, for example, a waiter robot, handling dishes after serving food. Eureka's automated training approach could enable virtually endless customization of robot capabilities. Any customer could potentially train robotic helpers for niche skills matched to their lifestyle, needs and preferences. In the future, one could imagine households having a general-purpose droid that gets tailored over time to cook favorite recipes, care for pets, maintain hobbies or assist elderly residents. Simulation-based training allows exhaustive exploration without real-world wear and tear. Industrial robots can be prototyped for new applications without any risk of damage. Entirely novel robot designs can be validated before physical prototyping. By making experimentation safer and cheaper, Eureka could significantly accelerate research and innovation in robotics. While Eureka automates algorithm generation, its training can be refined through human input to align outputs more closely with desired skills. As robots undergo training simulations, developers can assess whether the learned skills match expectations. Observed deviations can be used to adjust the task specification and regenerate improved training regimens. For example, if a robot fails to handle eggs gently, its rewards can be tweaked to place greater emphasis on care and precision. This iterative mechanism allows systematic alignment of training with intended goals. For complex skills, the reward algorithm itself could be exposed to human developers. This would allow interactive tweaking of reward magnitudes and conditions to steer training. As an example, the balance of rewards for speed versus stability could be tuned for a walking robot. This more granular involvement could help shape nuanced skills requiring extensive refinements. Blending Eureka's automated training with human supervision provides the best of both worlds. AI generates programs faster than humans while developers provide feedback to course correct when needed. Eureka shows the potential of leveraging large language models for robot training. Infusing more advanced successors of GPT-4 could exponentially boost Eureka's capabilities. As models grow larger and training techniques improve, associated gains in task comprehension and code generation prowess could tremendously expand the complexity of skills teachable to robots. Thus far, Eureka accepts text-based task specifications. Enhancing it to ingest other modalities like images, videos and speech could dramatically enrich context provision for training. For instance, showing examples of desired pen spinning maneuvers could help Eureka formulate suitable rewards and milestones. Inputs with greater contextual relevance could unlock training for more ambiguous, open-ended skills. A logical next step is transferring policies learned in simulation directly onto physical robots. Techniques for smooth virtual to real transitions would allow skills honed in digital environments to be seamlessly deployed in the real world. Advancing simulation to real transfer would enable rollout of Eureka robot training, from factories to flexible home and office settings. Thus far, Eureka teaches skills to individual robots. Extending it to train coordinating behaviors across robot collectives and swarms could enable complex collaborative automation. Construction or disaster relief scenarios involving dozens or hundreds of robots would become tractable by decentralizing Eureka's architecture. Eureka's dexterity breakthroughs need not be limited to physical robots. Adapting it to train virtual characters could significantly enhance CGI animation and digital art creation. Game design, visual effects and metaverse applications could benefit from more automated, AI-driven animation workflow. Eureka's training efficacy improves further when curriculum learning is applied, structuring training in a progressive sequence of rising difficulty. Training robots in the virtual Isaac Gym environment allows exhaustive testing of Eureka's algorithms before real-world deployment. Aberrant or dangerous behavior can be rapidly identified and rectified during the simulation stage. Eureka learns reward algorithms using a digital replica of the physical robot. Eureka's algorithms inherently incorporate safety considerations. We have been utterly amazed by Eureka's versatility in training robots for skills across the spectrum of precision and complexity in just hours or days versus months of human effort. It learns rewarding functions and curriculums tailored to each task that outperform the best human-crafted ones. Eureka's simulation capabilities allows prototyping and validating completely novel robot designs before building physical systems, enabling radical innovation with limited risks. Eureka's flexible training for diverse skills shows promise for transforming many realms. Some major industries and use cases likely to benefit include manufacturing, maintenance, safety features, household helper, and much more. For example, having multi-purpose robots that retrain swiftly for new tasks would make manufacturing and fulfillment operations vastly more agile. Eureka could make this achievable. Also, household helper robots trained by end users for personalized chores could become mainstream. Moreover, automating complex maintenance and operations safety procedures for aircraft, autos, and mass transit systems could be of great benefit. Robots could be adeptly trained for search, rescue, and stabilization missions. Custom unmanned vehicles and drones could be used more for risky intelligence, surveillance, inspection duties, and could also save more lives. Specialized robots could be made capable of adapting or discovering unknown environments. Current robots excel at structured tasks in controlled settings. But adapting them to messy real-world situations remains challenging. Eureka moves the needle, but generalizing its capabilities could accelerate ubiquity of intelligent robot assistants. Eureka provides a glimpse of the sensational innovations possible when AI and robotics intersect. Some broader trends and developments to look forward to in this symbiotic relationship are expanding iteratively from artificial intelligence. Recent times have seen emergence of substantially more expansive multi-purpose LLMs, like GPT-3. Eureka harnesses GPT-4 capabilities in a pioneering way for robotics. Future development of artificial general intelligence integrating reasoning, knowledge, and common sense could vastly enhance robot learning capacities. With exponential growth in computing power and smarter edge devices, cloud-based AI stands to enable advanced cognition for robots. Cloud robotics allows small, low-power robots to offload processing-intensive learning and inference tasks to the cloud. Shared AI models accessed by entire fleets of robots could accelerate skill acquisition. As this brief video reveals, integration of AI and robotics will catalyze remarkable technological shifts over the coming years. Core innovations like Eureka will pave the path toward more intelligent, dexterous, and helpful robotic assistants across many facets of life. Nvidia's Eureka represents a monumental advance in applying AI to train robots in sophisticated skills, bypassing the limitations of manual coding. By exploiting GPT-4's expertise at synthesizing algorithms, Eureka delivers revolutionary improvements in automation capabilities. Eureka's versatile simulations-based training methodology has enabled robots to match and even exceed human proficiency across a multitude of fine manipulation skills. Its self-improving architecture generates increasingly optimized training curriculums by analyzing outcomes of each digital experiment. Eureka represents a watershed moment in AI-empowered robotics. By automating algorithm generation for robot training via large language models, Nvidia Eureka overcomes perennial constraints faced by human programmers. Eureka's self-improving simulations-based method provides a versatile launchpad for imbuing robots with multifaceted skills. It paves the path toward more generalized automation transcending pre-programming. While Eureka's present feats are awe-inspiring, they constitute just the tip of the iceberg. Its approach could serve as scaffolding for channeling future AI breakthroughs into robotics advancement. Together with complementary innovations in cloud robotics, fabrication technologies, and human collaboration, Eureka is kicking off an era of increasingly intelligent and helpful automation. Nvidia Eureka embodies the tremendous synergies possible when AI and robotics intersect. As these fields continue co-evolving, we inch closer to the vision of flexible multi-purpose robot assistants enhancing every realm of life. Thank you for watching. That is a wrap. Until next time, stay curious, stay passionate, and most importantly, stay awesome. This is Make Money AI signing off. Don't forget to click the notification bell, so you never miss out on the newest updates in the world of artificial intelligence. Remember, every like, comment, and share brings us closer together as a community.